In this video, we're going to be talking about linear equations, and we're also going to introduce our first special type of function, which is the linear function. Let's start by talking about linear equations. A linear equation in x and y, in other words, containing the variables x and y, is any equation that can be written in the form ax plus by equals c. So a, b, and c are going to be actual constant numbers, and then x, y represents the variable relationship between inputs and outputs. One thing to keep in mind is the equation doesn't have to be originally given in this form. As long as it can be put into this form, then we consider it to be linear. So the important components are the x and the y, and the fact that they don't actually have any exponents on them. So the understood exponent on x and y is 1. As soon as we change the exponent on x or y, we change the structure of the equation and we no longer have something that's linear. So one of the important aspects of any line is its slope, which we typically represent by the variable m. So slope represents the steepness of the line, essentially. If we have a positive slope, then left to right, the line is sloped upward. If we have a negative slope, then left to right, the line is sloped downward. Slope is going to be an actual number representing steepness, so we need to be able to find slope. So slope is represented as rise over run. To get from any point on the line to another point on the line, it's how far we have to move vertically in relation to how far we have to move horizontally. This is a constant ratio for any pair of points in the line. Notice that as you would move from one point to another, if the points are close, it's going to be a smaller ratio. If the points are further apart, it's going to be a larger ratio, but they both reduce to the same fraction each time. So rise over run can also be expressed as change in y over change in x. That little triangle is the Greek letter delta. Delta just means change in. So change in y over change in x. And then if we have actual coordinates for points, that's going to be y2 minus y1, so the difference between the two y coordinates, divided by x2 minus x1, which is the difference in the two x coordinates, for any 2 points, x1 and y1, and x2 and y2 on the line. So let's practice finding the slope of a line given 2 points on the line. So we're given a pair of points, any 2 points on the line, and we want to find the slope of the unique line that's going to pass through that particular pair of points. So our first pair is -3, -2, and 2, 5. So first thing we want to start with is our slope formula, y2 minus y1 over x2 minus x1. One thing to keep in mind is whichever point we consider x1 and y1 and whichever point we consider x2 and y2 is arbitrary. It doesn't matter which one, whether we choose the first or the second. We just have to be consistent with our coordinates. So once we choose an x1 or a y1, the x that goes with that or the y that goes with it also has to have the same subscript. So in this case, let's consider the first point to be x1, y1 and the second point to be x2, y2. So for our formula, the numerator is the difference of the y coordinates, so 5 minus -2. Notice if I'm subtracting a negative, I need to be careful with my signs. And then my denominator is my x coordinate, which is 2, minus my other x coordinate, which is -3. So simplifying, I end up with 7 over 5, a positive slope. Let's try another one. So the points are 2, 3, and -1, 3. So in our slope formula, it's the difference in the y's divided by the difference in the x's. So 3 minus 3 divided by -1 minus 2. This simplifies to 0 over -3, which is 0. This is actually a special case for lines. Whenever we have a line with a slope of 0, this actually graphs as a horizontal line in the coordinate plane. Let's try one more. So we have -2, 0, and -2, 4. Using our slope formula, it's the difference in the y's divided by the difference in the x's. So 4 minus 0 divided by -2 minus a -2. So if we were to simplify this down, the numerator is 4 and the denominator is 0. Anytime we have a 0 in the denominator, this actual number is undefined. Conceptually, you can kind of think of this as infinity in a sense. Anytime the slope is undefined, there's something infinite going on. Dividing by 0 is a component of infinity. So in this case, if we were to graph this particular line, this is also a special case. It generates a vertical line. So slope is going to be a consistent component for any line determined by any 2 points on the line we find the same slope. So now let's talk about some different ways we can write linear equations. There are actually a bunch of ways to do this. We're going to look at three that are particularly important for our purposes. So the first form of a linear equation is called standard form. This is the form ax plus by equals c, the form we introduced at the beginning. A, B, and C specifically in this form have no common factors. In other words, suppose we had an equation like 2x minus 4y equals 6. This would not actually be considered a correct standard form because notice that the coefficients, all the constants in the problem, have a common factor of 2. So to get the correct standard form, we would divide out that 2 from each of the coefficients, and we would be left with x minus 2y equals 3 as our correct standard form. So let's look at a couple of examples. So we're going to be given a standard form equation of a line, and we want to find the x and y intercepts and then use these to graph the line. So our first line is 2x plus 3y equals 6. So first we want to find our x-intercept. Remember, the special thing about an x-intercept is regardless of what the x-coordinate is, the y-coordinate is always 0. So to find an x-intercept, we assume y is 0, and we solve for what x has to be in order to make the equation true. So 2x plus 3 times 0 equals 6. The 3 times 0 goes away, so we just have 2x equals 6, which means that x is equal to 3. So our x-intercept is x equals 3. Now let's find the y-intercept. So the special thing about a y-intercept is that the x-coordinate is always 0. So if we assume the x-coordinate is 0, then we can solve for the y to determine what makes that equation true. So we have 3y is equal to 6, or y is equal to 2. So we have an x-intercept of 3 and a y-intercept of 2. Anytime you're in the coordinate plane, as soon as you have 2 points, those 2 points uniquely determine a line. So as long as you have 2 points, all you have to do is connect those 2 points to graph the line. So in this case, we graph our intercepts, we connect those points, and we've generated a unique line. Let's try another one. So we want to find our intercepts and we want to graph. Our new equation is 2x equals negative 5y. Notice that this equation isn't technically in standard form, but in terms of the procedure used to find intercepts, it doesn't change. So let's find our x-intercept. So we want to let y be 0, and we want to determine what x has to be to make that a true equation. So negative 5 times 0 is 0, so we have 2x is equal to 0. Well, the only way this is true is if x is equal to 0. So our x-intercept is 0. Now let's solve for our y-intercept. So we assume x is 0, and now we solve for y. Well, 2 times 0 is 0, so we have 0 is equal to negative 5y. Divide by negative 5, and y is 0. So our x-intercept is 0, and our y-intercept is 0. We're in a special case where we have the same intercept on both the x and y axis. This only happens when the intercept occurs at the origin. The problem is that we only have one point. We need to find another point in order to graph a line. The good news is we can find any point we want on the line. Any other point is sufficient. So all we have to do is pick a particular coordinate for x and solve for the respective coordinate for y. You can pick any x value you want and you'll find a coordinate for y. So let's assume x is 10. Again, you can choose any x value you want. You're just going to get a different y value than the one we get. So if we assume x is 10, we're going to plug x equals 10 into our equation and solve for y. So we have 20 is equal to negative 5y. If we divide by negative 5, we get y equals negative 4. So another point on this line is the point 10, negative 4. So we can add that to our graph, connect the dots, and we determine our line. Now let's look at another form of a linear equation. This is called slope-intercept form, and it's the form y equals mx plus b. M is the slope of the line, and b is going to be the y-intercept of a line. So whenever you have the slope and the y-intercept of the line, you can automatically generate slope-intercept form. So this is the preferred but not essential form for graphing. So let's actually look at a couple examples where we determine slope-intercept form and then graph using that particular form. So we've got an equation that's close to standard form but not exact, but we want to determine slope-intercept form. So the major component of slope-intercept form is that y is by itself and everything else in the problem is simplified. So to take any linear equation and put it in slope-intercept form, the goal is just to get y by itself. So we've got 3y minus 6. First thing we want to do is move that 6 over. So I'm going to add 6 to both sides. So I flipped the equation, but it's consistently the same thing. So 3y is now equal to 5x plus 6. Now we want to get y by itself, so we need to divide by 3. Divide everything on both sides by 3. So with slope-intercept form, we have a number in front of the x, and then we have a constant tacked on to the end. So when we've got that 5x plus 6 divided by 3, we need to divide each of the terms by 3. So think of distributing that division to the 5 and to the 6. So if we simplify this down, we get y equals 5/3 x plus 6 over 3, which is 2. So this means our slope is 5/3 and our y-intercept is 2. So to graph, once we have a slope and y-intercept, first thing we want to graph is our y-intercept. So once we have the y-intercept, we want to use the slope to find another point on the line. Again, our slope is 5/3. We're starting at 2. So slope, again, means rise over run. It's how far we have to move vertically in relation to how far we have to move horizontally to get from one point to another on the line. So this means our rise, our vertical component, is 5 units. So if we're starting at our y-intercept at 2, we have to move 5 units vertically. But for every 5 units we move vertically, we also have to run or move horizontally 3 units. So 5 units vertically, 3 units horizontally, and that takes us to another point on our line. Connect the dots, and we have a line. Let's try another one. So we've got another equation that we want to put into slope-intercept form, and then we want to graph it using the slope and the y-intercept. So this is a substantially more complicated equation, but again, it is linear because there's an x and a y and they don't have any exponent on them. So even though it looks weird, it's still linear. Now, because we have denominators, we have fractions, it would be nice in theory if we could get rid of them. So we talked about this trick before. If you want to get rid of fractions, multiply through by the LCD. In this case, our denominators are 3 and 4, so the least common denominator for 3 and 4 is 12. So we want to multiply the entire equation, both sides, by the number 12. So if you distribute 12 on the left-hand side, the 12 and 3 will cancel, and the 12 and 4 will cancel, leaving you with coefficients in front of the x and y that are no longer fractions. So we're left with 4x plus 3y is equal to 12. So now we no longer have fractions. It's going to be a little easier to work with. Now, the goal is to put it in slope-intercept form, which means get y by itself. So we need to move that 4x over. So 3y is now equal to negative 4x plus 12. Notice I put the 4x out front and I just made it negative. Whenever we're talking about slope-intercept form, typically the x term goes in the front on the right-hand side. So if you're subtracting 4x, you can write it as a negative 4x out front and you're pretty close to slope-intercept form. Last but not least, we need to divide the 3 in front of the y. So divide both sides by 3. And then just like before, we're going to distribute that 3 to both components on the right-hand side. So negative 4 divided by 3 and 12 divided by 3. So we get y is equal to negative 4/3 x plus 4. So our slope is negative 4/3 and our y-intercept is 4. So graph the y-intercept on the coordinate plane. And then we're going to use the slope to find another point on the line. Just a reminder, the slope was negative 4/3. We're starting at y equals 4. So if the slope is negative, it means that our rise is going to be in the negative direction. As opposed to moving up, we're actually moving down. So our rise, our vertical traveling, is negative 4 units. So starting at y equals 4, we move down 4 units. Then for every 4 units we move down, we have to run horizontally 3 units in the positive direction. So we end up at a new point, which just so happens to be the x-intercept in this case. Connect the dots, and we have a line. Now let's look at our last form for a linear equation. This is called point-slope form. So point-slope form is y minus y1 is equal to m times x minus x1. So m is the slope, just like before, and then x1 and y1 generate any point on the line. So in order to use point slope form, just like the name suggests, you need to have a point and you need to have the slope of the line. So typically this is not a final form in terms of what something we would give as an answer to represent a line. It's an intermediate form used to find an equation. So if we're given information about a line and we want to find an equation of the line, as long as we can determine the slope, and if we're given any point that's on the line, then we have enough information to find an equation of the line. At that point, we can move things around, we can redistribute, we can do whatever we need, and we can put our equation into standard form or into slope-intercept form, depending on what we're looking for. So let's try a couple examples here. So we want to write the equation of the line described, given the information we're given, in slope-intercept form and then in function notation. So we'll talk about function notation when we get to that. So here's what we're given. We're told that our line passes through the point 2, -3, and it has a slope of -4. So we've got a point, we've got a slope, we have enough information for point slope form. So we're going to plug the given information into our formula, y minus y1 is equal to m times x minus x1. So notice on the left-hand side when we plug it in, because our y coordinate that we're plugging in is negative, I have to subtract a negative. I need to put parentheses around the number I'm plugging in. Subtraction is part of the formula, so when we're plugging in a negative number, we need to be really careful with our signs. So we plugged it in, and technically speaking, this is an equation of the line described, but it's not in the final form we want. We want slope-intercept form. So I have to simplify everything down, and then the goal is to get y by itself. So there's two major parts I need to simplify. I need to simplify that subtraction of a negative on the left, and then I need to distribute the -4 on the right. So let's do that. So we have y plus 3 is equal to -4x, and then -4 times -2 becomes a +8. Now I can get y by itself in one more step. I need to move that +3 over. So I subtract 3, and I get y is equal to -4x plus 5. This is our slope-intercept form. Now it also asked for function notation. The only thing we need to convert from slope-intercept form to function notation is to change our y into an f of x. Remember when we talked about functions, I said that anytime you see y, as long as you're talking about a function, y and f of x are interchangeable. So slope-intercept form is really just a one step away from function notation. So if you've got slope-intercept form and you want function notation, all you need is to change your y into an f of x, and then you have the form you want. Let's try one more. So we want to write the equation in slope-intercept form and then in function notation. Now we're given 2 points. Instead of being given a point and a slope, we're given 2 points. But we know we have a formula to find slope. So the goal is to use point slope. We need a point and a slope. If we're given 2 points, we can find the slope and then we can go from there. So let's find the slope. So you can use either point as 0.1, either point as 0.2, it doesn't matter as long as you're consistent. So change in y, 2 minus -6, over change in x, which is -1 minus 3. Simplify this down, we get 8 over -4, which simplifies to -2. So the slope of the line passing through these 2 points is going to be -2. Now when I want to use my point slope form, notice I have 2 points here. Which one do I choose to plug in? The answer is it doesn't matter. You can choose whichever one you want. I would say choose which point ever feels easier to plug in. Typically, if you have a point that has 1, 0 coordinate, it may be easier to plug that one in just in terms of what your simplification is going to look like. But you can pick either point to plug in for x1 and y1. It does not matter. So we're going to pick the second point just because the numbers are smaller, but again, you could choose either. It's not going to change anything. So plug in your point coordinates, in this case -1 and 2, and then plug in the slope of -2. We want to simplify everything down. The left side doesn't need to be simplified yet, but the right side definitely does need to be simplified. So subtracting a -1 is addition, and then we need to distribute the -2. So if we do all that, I did it in one step. Pause the video if you need. Go and try to do that in a couple steps. Make sure you get down to y minus 2 is equal to -2x minus 2. Now we need to get y by itself, so we need to add 2 to both sides. So we end up with y is equal to negative 2x. This is our slope-intercept form. Notice there isn't any number added or subtracted after the x term. That's okay. That just means our y-intercept is 0. There's an understood plus or minus 0 tacked onto the end. So if we were to graph this line is actually going to go through the origin. That's going to be its y-intercept. So its slope-intercept form is y equals negative 2x. To convert to function notation, we just rewrite that y as an f of x. So we've talked about the 3 different representations we have for linear equations. Again, their standard form, slope-intercept form, and then point-slope form. So now that we know about one line, let's talk about 2 lines. Let's talk about relationships we can have between lines. So one of the first possible special relationships is 2 lines are parallel. So parallel means they never cross. It means they continue forever and ever in the coordinate plane and they're never going to touch. They're never going to intersect. So technically speaking, lines are parallel if they have equal slopes. So the slope of the original line is equal to the slope of the parallel line. Any 2 lines that have the same slope are always going to be parallel. They're never going to touch. They're never going to cross. Essentially, they're going to look like equal signs in the coordinate plane. You can think of it that way. A couple special cases, horizontal lines are parallel to each other and the x-axis. So every horizontal line is parallel to every other horizontal line. One special horizontal line is the x-axis. So all horizontal lines, including the x-axis, are parallel. The same thing is true for vertical lines and the y-axis. So the y-axis is just a special case of a vertical line. Every vertical line is parallel to every other vertical line and the y-axis. Another special relationship between lines is being perpendicular. So 2 lines are perpendicular if they cross at 90-degree or right angles. The slopes are a little different in this case. Lines are perpendicular if their slopes are opposite reciprocals. So the way I remember this is flip the sign, flip the fraction. So perpendicular lines, one slope is going to be positive, one slope is going to be negative, and then the actual numerical parts are going to be reciprocals of each other. So one thing to keep in mind, say you have a slope that's a whole number. You can think of a whole number as something over 1. So if you want to find the reciprocal of a whole number, it's that number over 1, flip it, it becomes 1 over that number. So that's what a reciprocal looks like if one of the slopes you have is a whole number. And then a couple special cases again. Horizontal lines are perpendicular to vertical lines and the y-axis. And then vertical lines are perpendicular to horizontal lines and the x-axis. So let's look at a couple examples where we determine whether lines are parallel, perpendicular, or possibly neither. Keep in mind that parallel and perpendicular are very special cases. If you just randomly pick 2 lines in the coordinate plane, more than 99% of the time, they're not going to be either parallel or perpendicular. They're just going to be 2 lines that intersect somewhere in space. So just keep in mind parallel and perpendicular are special cases. They're not the norm. So here's our 2 lines. Remember, parallel and perpendicular are determined by slope. So what we care about is the slope of the line. What are the slopes of the lines we're given? Well, the easiest way to determine the slope of a line is by putting the line in slope-intercept form if it's not already in that form. Slope-intercept form is helpful because we determine the slope just based on the placement of numbers in the equation. So if we can put each of these equations into slope-intercept form, we can immediately determine the slope without really having to do any work. So for our first one, we need to get y by itself. So if you add y to both sides and then subtract 3, or you could subtract 2x and then divide by that -1 out front, either way, slope-intercept form you'll get down to is y is equal to 2x minus 3. So the slope of this line is 2. Now let's look at the other one. So we need to get y by itself. This one we can do in one step. So there's a 7 subtracted from the y. If we add it to both sides, then we immediately have slope-intercept form. So y is equal to -1/2 x plus 7. So the slope of this line is -1/2. Well, these 2 slopes are closely related. Notice one is positive, one's negative, and then they're reciprocals of each other. So one slope is 2. The other slope is the reciprocal of 2, which is 1/2. So these two slopes are opposite reciprocals, which means that these two lines are perpendicular to one another. If we were to graph these in the coordinate plane, then they're going to cross at a 90-degree angle. Let's try another one. So our two lines are 8x minus 5y equals 3, and 5/4 y minus 2x is equal to -1. So again, we want to determine each line's slope and then compare them. So we want to put our first line in slope-intercept form so the slope's easy to determine. We want to get y by itself. So move your 8x over, move the 5y over, whatever you want to do. We want to get the y term by itself. So once the y term is by itself, it's 5y is equal to 8x minus 3. Divide by 5. So y is equal to 8x minus 3 over 5, and then distribute that division. So y is equal to 8/5 x minus 3/5. So for this line, the slope is 8/5. Now let's look at the other one. So 5/4 y minus 2x is equal to -1. We want to get the y term by itself, so we can add the 2x to each side, move it over to the right. So 5/4 y is equal to 2x minus 1. Now we need to get rid of that 5/4 in front of the y. Conceptually, we're dividing it out. But if you remember, dividing by a fraction is the same thing as multiplying by that fraction's reciprocal. In this case, the reciprocal of 5/4 is going to be 4/5. So what we're actually doing is we're multiplying both sides of the equation by 4/5. On the left-hand side, the 4's cancel diagonally, the 5's will cancel diagonally, and on the right-hand side, we're just left with 4/5, which is going to have to distribute to the 2x minus 1. So distribute the 4/5, we get y is equal to 8/5 x minus 4/5. So the slope for this line is 8/5. Because our two lines have the same slope, these lines are parallel. Now let's put it all together. So what we know now about parallel and perpendicular, and what we know about finding the equation of a line. So our goal is to find the slope-intercept form and the standard form with lowest possible coefficients for the line described based on the information we're given. So the information we're given for this line is that it's parallel to -3x plus y is equal to 4, and it also crosses through the point 3, -1. So remember, when we're finding an equation of a line, we're using point slope. So in order to use point slope, we need a point and we need a slope. Well, we're given the point is 3, -1. We're not exactly given the slope, but what we are told is that the line we want is parallel to a line we know. So if we can determine what the slope is of the line we're given, then we can use that to determine the slope of the line we want. So let's first determine what the slope is of the line we were given. So we know we want something that's parallel to -3x plus y equals 4. Well, what's the slope of this line? Let's put this line into slope-intercept form. So we want to get y by itself. We add 3x to both sides. Y is by itself, which means the slope of the line that we were given is 3. Now we're told that we want a line that's parallel to this line, which means the slope we need has to be the same slope. So the slope for our line we want to determine is also going to be 3. So once we have a slope and a point, we can plug into point slope, and then we can find the equation of the line. So we plug in our y and x coordinate, we plug in the slope we just found, and then we know to simplify. So we want to find slope-intercept form. We have to distribute our 3, and we have to combine things, move them around a little bit. So y plus 1 is equal to 3x minus 9. Change that subtraction of a negative into an addition, distribute the 3. Now move that plus 1 over, so we have y is equal to 3x minus 10. And this is our slope-intercept form once y is by itself. Last but not least, we want to rearrange to find standard form. So our slope-intercept form is y equals 3x minus 10. We know standard form has x and y on the same side of the equation, so we need to move that 3x over to the left-hand side. So move the 3x over, that becomes -3x plus y is equal to -10. Now sometimes, depending on the context, we don't necessarily like to have a negative out front. So if we don't want the negative out front, one option we have is to divide everything in the equation by a -1. it's going to flip all our signs, so some things that were positive will become negative, but if the goal is just to get rid of the negative out front, then that accomplishes the goal. So if we do that, then we get 3x minus y is equal to a positive 10. That is another version of the standard form that is equally correct. Let's try one more. So again, same directions. We want to find slope-intercept form and standard form based on the information we're given. So now we're told that we want a line that's perpendicular to x minus 2y equals 7 and passing through the point 5, 4. So again, the goal is to use point slope. We've got a point, we need a slope. We're not given the slope, but we're given information about the slope. So first thing we want to do is determine the slope of what we're given and compare it to determine what's the slope we actually need. So we're told that we want to be perpendicular to x minus 2y is equal to 7. So let's determine the slope of this line we're given. We want to get y by itself, so we can subtract x, move it over. We have negative 2y is equal to negative x plus 7. Divide by the negative 2 out front. We get y is equal to negative x plus 7. Divide by negative 2. If you simplify that down, then we have y is equal to 1/2 x minus 7 over 2. Notice there isn't a 1 written in front of the x in the step before. It's implied. So if we want to write the slope as a fraction in front of the x, if there isn't anything directly in front of the x, you can assume it's just a 1. So the slope for this line, the one we were given, was 1/2. We're told we want a line that's perpendicular to this line. So the slope we need is going to be the opposite sign and the reciprocal of what we were given. So we had something that had a positive slope, we now want a negative slope, and then the reciprocal of 1/2 is going to be 2. So the slope we want is going to be negative 2. Now we plug into our point slope form given the point and the slope we just found. So y minus 4 is equal to negative 2 times x minus 5. Now we want to simplify, find our slope-intercept form. So we need to distribute the negative 2 and then simplify. So y minus 4 is equal to negative 2x plus 10. Add the 4 to both sides. We get y is equal to negative 2x plus 14. So this is our slope-intercept form. Now let's rearrange and find standard form. So we have y is equal to negative 2x plus 14. We can find standard form in one step. Again, standard form just means x and y are on the same side of the equation. So we've got a negative 2x on the right. If we add it to both sides, we can move it to the left. We have 2x plus y is equal to 14, and that is our standard form. Let's finish by talking about a couple applications of linear functions. Remember, to get a linear function, we take slope-intercept form and just replace the y with an f of x, and then we have something that's in function notation. So linear functions can be used to represent real-world situations that have variable and fixed elements. So something that changes based on another quantity versus something that's not going to change. So an example of some variable elements, commission or cost per unit. So if you think about car sales, something like that, that's familiar to a lot of people. Commission is how much you make based on how much you sell. So even though the commission amount is fixed, the more cars you sell, the more you're going to make overall. So commission is considered variable. Cost per unit, if we're talking about cost, would be like materials cost. So suppose we're manufacturing something. The actual cost per manufactured unit is the same, but the more things we manufacture, the more cost we have overall. So these two quantities are considered variable elements because the total amounts change based on how much we are producing or selling. Some fixed elements that correspond to commission and cost per unit are base pay and then overhead. So sometimes, depending on how a contract is negotiated, even though you make commission, you may have what's called base pay, which is essentially what you take home even if you don't sell anything. So you may have a fixed amount you get to take home regardless of how much you sell. This is fixed. It doesn't change based on how much you sell, so it is considered fixed. Overhead also corresponds to cost per unit. So overhead is the cost that you incur to manufacture regardless of how much you manufacture. Things like paying executive salaries or paying to keep your utilities on, those are costs you're going to incur whether you actually produce and sell anything or not. So they are considered fixed. So the general form of any linear function that represents a situation involving these kind of components is f of x equals mx plus b, slope-intercept form like we've seen before. So m is the variable part. It changes over time. So m times x is going to increase as x increases. The amount for the variable part is going to be the same, but as you increase x, you end up incurring more as m is multiplied by x. And then b is the fixed part. B is not going to change. Regardless of what x is, b is a constant amount and it's fixed. So for our example, we're going to consider the manufacturing situation. Specifically, we're going to look at cost, revenue, and profit. Those are three things you would consider in any situation where you're producing and selling some type of item. So we're going to generate three different functions, one representing each of these components of the business process. So cost, we're going to represent as C of X. Notice we're using a different name, but the name corresponds to what it represents, so it's a reasonable name. So we'll call it C of X. It's going to be of the form MX plus B. M is cost per unit, so it's how much we incur to produce an individual item. Once we multiply it by X, that'll be the total amount of cost we have for just production. And then B is going to be fixed cost, in other words, overhead. It's the things we're going to have to pay for regardless of how much we make. The second function is going to be revenue. We're going to call this one R of X. R of X is equal to P times X, where P is the price charged per unit. So notice that this is completely separate from the cost function. We make a certain number, we sell a certain number, and then we multiply by how much we're charging our customers, and that represents our revenue. Think of revenue as just the amount in the cash register at the end of the day. And then finally, we want to talk about profit. Profit is the really important part. So profit is going to be represented as P of X. Profit is going to be revenue minus costs. So if you think of it in terms of a cash register, you make a certain amount during the day, and suppose you pay all your bills at the end of the day. So you take the money out of the cash register, you pay off all the costs you had for the day, whatever's left over represents profit. So let's look at a specific example. So it says, an outdoor summer concert, a vendor sells fresh squeezed lemonade for $2 per cup. The cost to rent the booth for the day is $120. Furthermore, the vendor knows that lemons, sugar, and cups collectively cost 50 cents for each cup of lemonade produced. So this is our scenario. So first thing we want to do is we want to write a linear cost function, C of X, that models the cost of producing X cups of lemonade. So what we need to determine is the components that go into this cost function. What numbers represent elements of cost? We've got $2, we've got $120, we've got 50 cents. We need to know which one corresponds to which. So in this case, our variable cost is 50 cents. It's the amount we have to pay in order to make each of our individual products. So for each cup of lemonade we make, we have to pay 50 cents to our suppliers. And then B, our fixed cost, is going to be $120. Regardless of how much lemonade we sell, we have to rent the booth. So we have to pay $120 regardless of whether we make and sell any lemonade or not. So that's considered our fixed cost. That means our cost function, mx plus b, is going to be 0.5 times x plus 120. Now let's look at our revenue function. So we know lemonade costs 50 cents to make, the booth costs $120 to rent, and we also know we're selling our lemonade for $2. So P is going to be $2. P is the price we sell our lemonade for. So revenue is P times X, which in this case is going to be 2 times X. Finally, let's look at our profit function. So profit is described as revenue minus cost. We determined our revenue function, we determined our cost function, so we just take the difference between the two. Simplify this expression down, and we have 1.5x minus 120. So one thing we need to take into account that we haven't mentioned before is that x in terms of how much we're making is also the same as x in terms of how much we're selling. In other words, we have to think of our business as a make-to-order business. However much we make is the same amount as however much we sell. It's not as simple of a situation if you make a bunch and then maybe you don't sell it all. Unfortunately, we can't simplify things as easily if that's the situation we're in. So for our purposes, we're assuming that every single cup of lemonade we make, we also sell. That way we can directly relate profit as revenue minus cost. So let's use this profit function. What would it be used for? So first question we want to answer, how much profit will the vendor make if 50 cups of lemonade are produced and sold? A profit function, again, takes an input, which represents how many cups of lemonade we're making and selling, and it gives us the related output, which is how much profit we get to take home at the end of the day based on how much we made and sold. So if we want profit for 50 cups of lemonade, that's going to be P of 50. So we take our rule for profit, we plug in an input of 50, simplify the expression down using a calculator if necessary, and we end up with negative 45. So if we want to think of this in the context of the problem it's actually in, negative 45 means we're losing money. It means we're not profitable. In other words, we didn't make enough to cover both our variable costs and then the fixed cost we have for renting the booth. So let's try another one. Same profit function. How much profit will we make for producing and selling 128 cups of lemonade? So we want to find P of 128. When X is 128, what's the output? What's the profit we're making? So we plug in 128, simplify the expression down, and we get an output of 72. Because this is a positive number, our profit is positive, it means we are profitable, we are making money. So if we make 128 cups of lemonade, we're going to have some money to take home at the end of the day after we pay for our supplies and after we pay for the booth. Last but not least, let's determine the break-even point. Break-even means you're not losing money, but you're not making money. Essentially, everything that goes into the cash register has to be taken out and used for bills. So break-even means profit is 0. Well, profit is represented as P of X. So set P of X equal to 0 and then solve. So P of X is 1.5x minus 120, so that's equal to 0. We want to know, what does X have to be to make that equation true? Move the 120 over. We have 1.5x is equal to 120 divided by 1.5, and X is equal to 80. So if we want to put it back into the context of the problem, how many cups do we have to make in order to break even, in order to neither lose money nor make money? We have to make 80 cups of lemonade. So we're making 80 cups and we're selling that 80 cups of lemonade. To summarize, slope defines a particular component of the line. Slope describes the steepness of a line. So how tall is the line? Is it going upward left to right, or is it going downward left to right? So slope is usually expressed by the variable m. M represents rise over run, so vertical change versus horizontal change to get from one point to another. If we have 2 points on the line and we want to find the exact slope, it's the difference between the y coordinates and the points divided by the difference in the x coordinates for those 2 points. We have 3 forms for linear equations. The first form is standard form, ax plus by is equal to c. So x and y are on the same side of the equation. A, b, and c are going to be constants. Typically, we like to express a, b, and c as relatively prime numbers, which means that a, b, and c shouldn't have any common factors besides 1. In other words, if we can divide out anything that a, b, and c have in common, then we should do that. Our second form is slope-intercept form, y equals mx plus b. M represents the slope of the line, b represents the y-intercept of the line. This is typically going to be the easiest form to use for graphing. And last but not least, we have point slope form, y minus y1 is equal to m times x minus x1. So m is the slope of the line, and then x1 and y1 are the coordinates of some point on the line, any point we want. So point slope is not typically an equation form used as a final answer. It's an intermediate form used to get to slope-intercept form or to standard form if we're given information about the line and we want to find an equation. And finally, we have some special relationships between lines. Again, they don't occur very often. 99% of the time, neither of these will occur, but sometimes they do. So parallel lines have equal slopes. They never touch. They go side by side forever and ever on the coordinate plane, and they're never going to cross. And then we also have perpendicular lines. But lines are perpendicular if their slopes have opposite signs and are reciprocals of one another.